Lab 6 Magnetic Molasses. So the purpose of this lab is to investigate Faraday's law by observing the effect of dropping a magnet down a conducting tube and comparing these observed results with a computational model. Key concepts were Biot-Savart, Faraday's, and Newton's second law, and the main results were that the observed time to fall on average was 1.178 seconds, while our theoretical time was 1.373 seconds. First fundamental principle, Biot-Savart law, states that magnetic fields caused by moving charges can be quantified according to that equation. And Faraday's law states that changing magnetic flux induces an EMF in a closed loop. And finally, Newton's second law states that force is proportional to mass and acceleration, and when net force is zero, we can see that there's static equilibrium and we have a balance of forces. So for initial conditions, the magnet is dropped at time equals 0 at the top of the tube from stationary, and our system is the neodymium magnet, while our surroundings is the aluminum tube and the environment. First, our aluminum foil roll was used as a conductive tube, and the dimensions of the tube and magnet were measured. Person 1 held the aluminum tube vertical and dropped the magnet down the tube, while person 2 recorded the tube for the duration of the fall. Steps 3 and 4 were repeated 4 times for 5 trials, and finally the video was scrubbed to obtain the fall times as the magnet fell in the tube. As you can see, for trials 1 through 5, our time in and time out of the tube were recorded, which gave us a couple of fall times for each trial, resulting in an average time of 1.178 seconds. And on the left, our dimensions of the aluminum tube and magnet are stated. Our magnetic moment of 3.68 was obtained from lab 4. Our computational model starts off by creating the aluminum tube, which is approximated as many rings stacked together. We create the magnet and also the magnetic flux function. And finally, we simulate the falling magnet using a while loop. And the computational model's visual shows the magnet falling on the left and gives us a theoretical time of 1.373 seconds. And it also gives us a velocity versus time graph where we can see that the purple region has a constant velocity, therefore we have a balance of forces. So which color corresponds to which current direction? Well, according to Lenz's law, if our dipole moment points up as the magnet is dropped, the red current is our counterclockwise current, while our blue is the clockwise current. What happens if we flip the magnet around? Well, the dynamic behavior does not change, as our induced dipoles always oppose the falling magnet. So how does our total fall time of our real-world system compare to our computational model? Well, our real fall time was slightly faster than predicted by the model, and prediction could be improved in accuracy by accounting for error sources and inputting more accurate measurements. So how does the shape of the V versus T plot tell you about the forces? Well, inside the tube, forces balance out, resulting in a constant velocity, as we saw earlier in the purple region with a flat line. Outside, our magnet simply accelerates due to gravity. For our results, our magnet fall times are stated again, and this gives us a percent error of 14.2%. For our assumptions made, our air resistance was negligible, our magnet is an ideal dipole, and our aluminum foil is a perfect cylinder/tube. Some potential error sources were the magnet colliding with the tube walls, timing imprecisions, and environmental factors such as external fields. If the resistivity was as close as possible to zero, the lower resistance would allow more current to flow, resulting in a larger induced force, and our magnet will fall slower. If holes or slots are cut into the tube, this would be effectively cutting some of the rings of the foil as modeled, not allowing current to flow. This would result in a weaker net induced force, allowing the magnet to fall faster. So the main outcome was that we were able to compare observed falling times of a magnet with a computational model, but the computational model overestimated our fall time compared to real life. This is likely due to the non-ideal conductivity of foil roll due to the geometry of the messy, loose rolling and the chaotic motion as the magnet tumbled. Our accuracy could be improved by using a solid metal tube and a precise release. Thank you for watching.